at this simulation here. Online, you're seeing this online? Online, you're seeing the screen? Right, it's supposed to be a cell simulation there, right? Hello, online? Anybody online? Anybody respond to that? Right. Okay, nice. So our focus today is to focus on how gas particles really behave, right? So look at this simulation. All right, so watch this here. I'm going to put in some gas particles, and I'm not sure if you all can see clearly, right? But I want you to pay attention. Pay attention to pressure. Tell me what you're observing, right? Watch it carefully. It might be a little bit slower, one line. Hold it, right? You could always go to the length. Pay attention to the pressure value. Right. Nice. So take a look there. Right, yes. So I want you all to recognize the pressure value was initially what? Was 0, right? And when I dropped all the particles in there, the pressure went up to like around 5.6, 6.1, right? So look at the gas particles. What you all notice about the gas particles? Right. So they're moving randomly and they're hitting the side and they're hitting each other. And you will recognize that the pressure kind of fluctuated. I'm going to put in some more particles. Why so slow? Right, I'm putting in some more particles. And what I'm doing the pressure value? Much higher, right? So could you all give me a little idea of what you think controlling the pressure? The more particles I have, the greater the pressure, right? So, but what it is happening with particles? They're randomly moving and you're seeing more what? You're seeing more collisions, right? So because you're seeing more collisions, there's an increase in pressure. What does that say about collisions and pressure? How are they related? Directly. They're directly related. So the more collisions we have, the greater the pressure. You're seeing that? So I want to reset it again. I want to reset it. Where is that? Was reset. Right. I want to do something else. Anybody can tell me what else I can do? So we just learned that collisions equal pressure. How can increase pressure again? Raise the temperature. Who said that? Very good. I can raise temperature. So I want to heat it up. I'm going to heat it up. But what happens in particles? They're moving faster, right? And what happens to the pressure value? Going up. So if they move faster, they're doing what more? They're doing what more? More collisions. Very good. More collisions. More collisions, greater pressure. You're seeing that? Let's reset. One more thing. Let me put some red people in there now. Oh, the red small. Right. Oh, the red are active boy. What else I can do? What else I can do earlier? Make the box smaller. Isabella pointed in. Very good. Isabella said to make the box smaller. Pressure went up. What's it good? Why? More room? Right. Less room so they collide more. Right? Less room so they collide more. Right? So Amelia taught us about temperature. Isabella taught us about volume. And initially I showed you all up with number of particles. Everybody okay with that? So what is kinetic theory? Kinetic theory is the random movement of particles. Right? Because of this random movement, Ashish, there's always this collision. There are always collisions. And we can see here that collisions equal pressure. All right? I want to play around with one more thing before we go. Actually, I'll pause it here and let's go. Let Vinaya give us a little note. So we need a small note, right? Let's take a look at kinetic theory. This in your handout, but I know some of you might never open the handout. So let's just talk about kinetic theory. Right? The focus really is gas particles. Right? Yes, it has solids and liquids, but in physics, we mainly focus on kinetic theory of gases. So we said that if we have a container and the container has gas particles in here, those gas particles move randomly. So the first thing we could say is that the particles move randomly, right? Particles move randomly. Second thing we could say, because they move randomly, what keep happening? Collision. Right? Matthias, your mom called for you and I tell see you leaving now. I thought you went to. You didn't tell him Maria was going anywhere? Oh, I thought she called. I thought she going home. Well, I can't tell her that. No, but I'm joking. Well, they only had 10-minute break. Well, I went quite on well, don't go there. Don't go there. Go downstairs in the cafe or otherwise buy some water and hold up, right? Constantly collide with who? Who they collide with? And the walls of the container. Constantly collide with themselves and the walls of the container. Right? There are more kinetic theories like they will be Newtonian mechanics and so on, but this is what I'm interested in. Constantly collide, they move randomly. 2 words I want to remember. I might remember the whole definition, but I want to remember the 2 words, right? Okay. Right, so you have 10 minutes. Wait there will not work out. All right. And then when we looked at the simulation, we learned that collisions equal to pressure. Right? Collisions equal to pressure. Collisions equal pressure. Sorry, ma'am. Right. And I showed you all 3 ways. I showed you all 3 ways to increase the pressure. Can you all write them? What are the 3 ways to increase pressure? Write the 3 things that increase pressure. Write the 3 things that increase pressure. Three things increase pressure. And then we're going back to that simulation again. What I read my hand out to be. Yeah, supplying. Right, Manaya, has Maltiana.
Yeah.
All in 3 things?
Make the toilet box smaller, add heat and I have particles.
Okay, I don't like none. We'll try the last one. So the first one is said what?
I mean,
Right, yes. That's what I want to hear. I like that. Right, decrease volume of container.
I just said explode.
No, you said something else. What I said here?
I think.
I don't like heat.
Increase temperature.
Increase temperature. Very good. Increase temperature. What's the last thing? Right, increase the number of particles. Increase the number of gas particles. So that can work, right? Those are the three things that would increase pressure. All right. So if we look at the handout, we have a few things to try to explain, right? Go back to the handout. Four easy questions. You all remember dining, you all remember Brownian motion?
Yeah.
All right.
Okay, good.
Right, so go back to the handout, and there are four small questions here.
Until physics.
Yeah, same term out there.
I eventually called.
Try this one up, please. Why do you think that will happen? A ball, any kind of ball, a football. A football. So if you take a football, if you take a football and it's deflated and it's going to be stuck, why does it appear inflated? What does he do?
It will make
Right. So when it's placed in the sun, when it is placed in the sun, right, the temperature will increase, the particles gain more energy and collide more. Okay, and it will increase the pressure. No, the answer is not there.
Increase.
Right, so when placed in the sun, write it down so you will have it. When placed in the sun, the temperature in the ball will increase. Temperature of the ball will increase. This gives the particles more energy. This gives the particles more energy. Hence, they move faster. Hence, they move faster. Hence, they move faster and collide more. And collide more. Increasing the pressure in the ball. Increasing the pressure in the core. Increasing the pressure in the core. Right, try number 2 and 3 and 4. Try 2, 3 and 4.
Oh, yeah.
Finish them? Try to give explanations to each one, right? So I really wrong again, right? Yes, we put 2 and 3 and 4.
Again, that's not a picture. When? Yeah.
All right, let's go. Number 2. Why does placing more air into a tire increase pressure? Yes, Sydney? What happened? Very good. Right, so by placing more air, you increase the number of particles in the same volume, which will increase the number of collisions. Right? So same volume, more particles, you increase pressure. Right, more particles, make sure in your answer you have more particles, more collisions, more pressure. That's okay? Number 3. How can the pressure inside a hot can of soda be reduced? Yeah? Very good. Right? Right, so, right, what you can do, put it in the fridge. That will lower the temperature and lower the energy of the particles. Less energy, move slower, collide less. Yeah? Right, so you can open it slightly and reduce the number of gas particles. If you reduce, less collisions, less touch. Right? So you can open it slightly and reduce it, right? Right, Vinaya, over here, number 4.
A hole in a bicycle tire reduces pressure because air molecules escape to the outside. Therefore, the number of particles inside the tire decreases. Hence, fewer particles hits the walls of the entire thing. And it therefore needed to increase in pressure.
Right. So the hole will reduce the number of particles. If you reduce the number of particles, less collisions, smaller pressure. That's okay? Nice. Gus, about that? Yeah. Right, here's what we're going on to now. We are going on to something called the we are going on to something called the gas laws. So we're going to take a look at how 3 quantities are related. Right? We're going back to the simulation. Right, online, you'll see the simulation again. Ready? Online, you'll see the simulation. Right. So we need to observe how pressure, volume, and temperature are related, right? But here's what we're gonna do. We're gonna keep some of them constant, right? So in our first experiment, we are going to, where can I write? Right. We are going to see how pressure and temperature is related. by keeping volume constant. Right. Vinaya.
Sorry.
Right, Vinaya. Here's what we're doing. We're keeping volume constant. How do you think pressure and temperature are related? If we keep volume constant. Huh? So, they are saying loosely. What do you think? What will happen if we increase the temperature? Right? So what you say, right? Let's see what will happen. We're going to drop in some particles. Real slow. Right? We want to see how pressure and temperature are related, right? So I'm going to increase temperature. So if I increase temperature, what is happening to the pressure? Going up as well, right? So how are they related? Directly so far. And if I drop temperature, pressure will also drop. Right, nice. So here's what we learn. Okay. Sorry, that was nine. Right, so what does that mean? It means pressure is directly related to temperature. Whose law is that? Sorry, you're all in that. Sorry about that. Right? They're directly related, right? They are directly related. How do I write this as a formula? As a formula. P is equal to, very good. P is equal to K T. Or I could say K is what? K is P over T. Right? K is P on T. Right? Sanjay, yeah? Where's the yeah go? Sure.
Yes.
Right? This law is called pressure law. Right? I'll give you, they in your handout and I'll let you write them now. I'll write them over for you that's now, right? That's the first one we investigated. Let's try a next one. Oh, who want to write? Go ahead. Then I'm gonna give you back again, but we're gonna write it for now. Right? This is Boyle's law. Sorry. I don't know how it is. Pressure law. Pressure. Yeah. Pressure law, right? PV is constant. Not Kelvin. Kelvin is a unit. It's upon his P. Also, now you can tell. Right, so head up pressure law, and you can write that thing in blue, and I'll write the formula here for you. The formula is actually P1 and T1 staying constant, so you write P1 and T1 is equal to P2 over T. P1 and T1 is P2 and T. Copy that down? That is your pressure law. Put them back. Haven't taken a forward to put that on to do it now. So they had to get somebody to walk with it. But I have that color. There's a force now, I think, inside. One little lock, and then jump over, and then it's clear. Yeah, it's that going. I get to the door right there. Right, next one. Let's pause it there. Right, analyze. Tell me what you think will happen here. Let's go with Adrian. Adrian, you know how to give you one, right? Adrian, we need pressure and we need to learn about volume. And I'm going to keep temperature constant. Right? So I don't want to change temperature. How do I do that here? Pull something up. Why can't I keep temperature? Right. Here's a way to figure out Adrian. Check up. Oh, before please. Right. I want to adjust the volume and I want you to tell me what will happen to pressure. So here's what I'm gonna do, right? Here's what I'm gonna do. I am going to take the volume and I'm gonna make the volume smaller, Adrian. What do you think will happen with the pressure? Will it get bigger or smaller? Way bigger? Let me see. Let me see it, Mr. Adrian, right? So I'm gonna make the volume smaller. Did the pressure go up? The pressure was 3 and now it's gone up to. Now it's going up. Right. Now it's going up. Very good, Adrian. Adrian said it would increase. What would happen if I increase the volume, Ashish? Pressure will what? Pressure will drop. Very good. What type of relationship is that, Lucas? No, directly was the last one. Inversely. Pressure is inversely related to volume. Copy that down or write the formula for me. This is called Boyle's law. Boyle's law. Boyle's law. Boyle, yeah, Boyle's law. Copy that down. Copy that down, write the formula.
Oh, I like that. That's right. Very good.
Ooh, it's a curve. It's swallow, is he? No. Oh my God.
All right. I'm gonna take this off, right? Right. Everybody watch here. So far we learned about Boyle's law. We learned about Boyle's law, and the Boyle's law said that pressure and volume are inversely related at constant temperature. Right? And I gave you the worded version in the handout, right? And then we learned about pressure law. What did pressure law say again? Pressure was directly related to temperature. At constant what? At constant volume. Now we have one more to look at. It's a little bit trickier to see there, but I want to ask some questions about this one, right? Oh, by the way, let me write the formula for you one time. Right, the formula here was P1 T1 P1 T1 is equal to P2 T2. What did this formula turn out to be? Anybody work it out? Work out K from it. Anyway, don't worry, write this. P1 V1 is P2 V2. So we looked at these two laws, but Charles' law a little bit trickier. Charles' law. Charles' law is whenever we want to keep pressure constant, we alter in volume and temperature. I want to see how they're related. All right. So I want to ask a question. Anybody can answer. Suppose I give you a container and I have gas particles in here. And I heat it up. So I increase the temperature. If I increase temperature, but I want to keep pressure the same, what do I need to do? Think about it first before I answer. Listen again. Pressure must stay constant. I can't change it. Right? And I increase temperature. What do I have to do to keep pressure constant? Huh? Decrease the volume or increase? Increase. So if I make the volume larger, what will happen? Right. If I make this space larger, then I have more space with these high energy particles. So the pressure will stay the same, right? Right. So you don't want it to go up. Yeah. Hello? Yeah. Outside, okay, all right, then go on. Everybody okay with that? So when I increase temperature, the only way I could keep pressure the same is I have to make the volume larger. More space, so these particles will be excited, move around, and they'll collide less. So how are they related? How are they related? Directly. Turn this into a formula for me now, please. That's one drop some. Turn that into a formula.
But yeah. You want to go on? B1 over T1 over T2. But I think it's going out the line. That's gonna be. What time did it get? Yeah, maybe. Yeah, yeah. And if you do it, take that first, that's it.
Right. What's the formula you all came up with?
T1 over T.
Very good.
T2 over
V1 over T1 is equal to? Right. So what you will recognize here is that we end up with three laws. These three laws are called the gas laws. Right? They let us know, these are the gas laws. They let us know how pressure and volume behave and temperature based on the following conditions. That's okay? So if we keep pressure constant, it'll behave like this. If we keep volume constant, it'll behave like this, and so on. But suppose we not keep it anything constant. Suppose we keep nothing constant standard time. Suppose we keep nothing constant. What's the relationship we could come up with? Nothing constant. Everything that's manipulating altogether. Volume and pressure and temperature. What do you think will happen? Do you all think these rules will change?
Yeah.
You think they will change? You think if we increase temperature, pressure will go down?
No.
No. So pressure will always be if I put in nothing constant, right? Man, it's in real bad. Pressure is proportional to temperature. Yeah. What do you all think? So this will Matthias. Alright, I call him right? Right? What do you think about pressure and volume? How will it be related?
T1 and B1.
They will still be inversely. What do you think about volume and temperature? How do they be related? Right. So how do I put this into a formula? Watch this here. If I combine, look at these three formulas, and I combine them together, will they look like this?
PVT.
It's called the general gas law. Yeah.
PV over T. No.
P V over T. Excellent, Benaya. That's it. P1 B1 T1 is equal to P2 B2 That's the formula, right? If we combine this, it will look like that. Right? This is called the general gas law if nothing constant. Very good, Banana. P1 B1 T1 is P. You'll sign up for the thing like that, one like that.
Next.
Canadian example, what other example?
I think one of the
Yeah, you can do
Oh,
that.
that's true.
I did it. I signed up and I missed it.
Those punches over.
Oh, yeah, you have to ask for that now. We go one. Oh, yeah, see that, no, right. So this is called general gas law. When you're using this, nothing constant. All right? Right, Adrian? Right? And there's one more thing I want you to notice, Ashish. Is that besides, don't be on your phone, temperature is always zero. You get a chance to say it here.
In Kelvin.
In Kelvin, very good. You get a chance to say it here. We always measure temperature in Kelvin all the time. All the time. We don't ever use degrees Celsius. Ever. All right? So we have some small calculations and then we jump into this next week, right? That's what I'm focusing on. All right, online. So these are the 4 laws that we need to learn. Boils, charge, pressure, and general. Right, try these 3 questions and we are done. Try them fast, A, B, C, D. Fast, Olive. What's the formula you're using in party? Whose law are you using in party? Sasha. Whose law are you using in party? Charles' law. Okay, good. Hurry up.
Yeah.
Yeah.
What do you guys think about it? When I eat.
B. B and stuff on pressures.
294. Okay, this is P1. P over P. Yeah. Right. Okay, this P. Oh, it's not right. It's P off of any. Yeah. 25. I got 5. P is in here. Reason I usually want to see as fast. Oh, there. Oh, that's P1.
Right, first one was what? Whose law? The first one was Charles' law. How much you all got for T2?
490.
Work it out. Hey, John. How many go now? Work out. Yeah. How much you all got for T2? 490. Does it make sense? We balance it out. One up or one up? One up. Volume went up, so should go up, right? 490, correct? Part A is 490. Get us thus. Part A. Why didn't work out? Got up title. T1, T1. Right. So, I have tried it all there quickly.
Oh, that's 1, 3, 4, 7, 5, 6, 8. Most of them. 8, 9, 25.
Josiah, you all getting through? Well done. Right, so for the second one, for part B, which law you all use? Constant volume means the pressure law. P1 is equal to P2, T2. P1 is 125, P1 is 245, P2 is 150, and T2 is what? We gotta find it. I solve that two fractions equal sign here. Cross multiply. So you'll get 125 T2 is 150 by 150 by 245, right? And then make T2 the subject. That'll be 150 by 245 all over 125. Cross multiply, work it out. How much you get there? 294 Kelvin, right? So the answer for part B was 294. Right? So I use the pressure law. What you all got for C? 10.42. Anybody else got that? 10 point, good job, Shana. And last one, C was what?
239.6.
239.
Was 555.
For the first B2. Oh, sorry. They gave us B2. All right, sorry. Yeah, B2 is what? 23.
239. T2. T2.
Yes, T2 of course. 239.6. All right. Nice. So it's easy once you figure out the formula, right? Come on, so what's all the working, right? Okay, John, before you leave, make sure all the working. All. Right? All right, so next day we're doing the same thing. Please remember it, please. When you go downstairs to your break, and take in 10 minutes, breathe over the gas stove. Okay?